Jumping right into our integrated design project, we will be discussing each courses starting from Reaction Engineering 1, Process Modeling and Simulation, and lastly Separation Process 2. Two reaction types that occurs in steam methane reforming process is steam methane reforming SMR and water gas shift WGS. SMR is strongly endothermic, and the two types of reaction that occurs in SMR converts methane and steam into hydrogen, carbon monoxide and also carbon dioxide. Then carbon monoxide is further processed in a WGS reactor, which comprises of high temperature shift and low temperature shift. The reaction that occurs converts carbon monoxide and steam into hydrogen and carbon dioxide. Project, we chose a tubular packed bed reactor for our reactor design. It comprises of several tubes packed with a particular catalyst. The advantages are it has a high conversion per unit mass of catalyst, a low operating cost, continuous operation, and the disadvantages are the formation of hot spots, poor temperature control, and channeling may occur. The catalyst that we chose for our SMR reaction is a nickel-based catalyst supported by magnesium alumina oxide. For our WGS reactor, we have chosen iron chromium and copper-based catalyst for HTS and LTS respectively. The reasons are shown below in the table. The flowchart below shows a simple design of our reactor separator system, alongside the reactor's temperature, catalyst, and the chemical reaction that occurs. Assuming that a highly purified methane and steam is supplied in excess to the reformer, it then undergoes steam methane reforming at 700 degrees Celsius under the presence of a nickel-based catalyst to produce thin gases such as carbon monoxide, carbon dioxide, and also hydrogen. This reaction is strongly endothermic. Then, to increase the hydrogen yield, carbon monoxide is further processed in a WGS reactor, which comprises of a high temperature shift and low temperature shift that operates at 350 degrees Celsius and 200 degrees Celsius respectively. This reaction is then assisted by a catalyst such as iron chromium and copper-based catalyst. The remaining product is then sent to a separator for further purification of hydrogen for commercialized use. Smart, we have proposed 4 strategies to further maximize the selectivity and yield of hydrogen. Firstly is to increase the SMR temperature. As you can see by the graph, it shows the relation of methane conversion and hydrogen yield with respect to temperature. As the temperature increase, methane conversion and hydrogen yield also increase. This is because SMR is an endothermic process, meaning that it absorbs heat and it favors a forward reaction. This also means that delta H of SMR increases as the reaction temperature increases. Strategy is to decrease the SMR pressure. The graphs show a relation of methane conversion and hydrogen yield with respect to SMR pressure. As pressure increases, methane conversion and hydrogen yield decreases. This is because in general, SMR reaction favors a high temperature and a low pressure. Also, Le Chatelier's principle states that by reducing pressure, equilibrium will shift in the direction in which it will counteract the effect, resulting in increase in hydrogen yield. The strategy is to increase the ratio of steam to methane on the feedstock. The graphs show the relation of the reforming product, hydrogen to carbon monoxide with temperature. As you can see, different hydrogen to carbon monoxide ratio is denoted by different colors. At lower temperature region, a higher H2 to CO ratio is obtained. This is because in WGS, LTS is more favorable at low temperature, which increases amount of hydrogen and decreased amount of carbon monoxide. Alternatively, as the temperature increase, which denotes a high temperature shift, it results in higher amount of carbon monoxide. Therefore, lower H2 to CO ratio is obtained at higher temperature. A strategy is to utilize another type of reactor, which is called a fluidized bed membrane reactor or FBMR. The advantages of an FBMR is the flexibility in placing the membrane. It can also facilitate an isothermal operation with negligible pressure drop. The disadvantages are the possible formation of stagnant zones, and membranes may experience mechanical stress, and also it is a complex construction.
The last section of reaction engineering is the sizing of reactor and calculations. The assumptions made and the properties of SMR and WGS reactor are shown as above. First step is to calculate rate constant K with the kinetic data based on reference by using the Arrhenius equation, which obtains 0.1514 per second. Stoichiometry table is formed with 4 species: methane, steam, carbon monoxide, and hydrogen. In a species is absent as pure methane and water is used. The sigma obtained is 2 and YAO is 0.2381 while YBO is 0.7619 based on the assumptions of molar flow rate A is 3600 kmol and molar flow rate B is 11520 kmol per hour. Next, theta B obtained is 3.2 while theta C and D is 0 as C and D are products. Expansion factors of 0.4762 is calculated as gas phase is present. The acetylene molar flow rate and concentration is calculated based on stoichiometry table. Last step is to calculate the catalyst weight and reactor volume by deriving W equals FA naught divided by negative RA multiplied with delta X. Initial volumetric flow rate is determined as 33557.0470 decimeter cube per second and catalyst weight obtained is 5.53 times 10 to the power 5 kg. The same steps are implemented for WGS reaction. As the sigma obtained is 0, no expansion factor is needed for the calculations. For HT shift, the weight of catalyst obtained is 1.1298 times 10 to the power 9 kg. For LT shift, the weight of catalyst obtained is 2.0559 times 10 to the power 9 kg. Moving on to process modeling and simulation, let us look at the simulation setup for SMR and WGS reaction. Assumptions made are natural gas contains only pure methane as fuel. The syngas exit the reformer at reformer operating temperature and pressure. All gases mixture are stimulated as mixture of ideal gases. Packed big reactor PBR is assumed to be plug flow reactor PFR in this simulation. Mixture in reactor is perfectly mixed and no heat loss to the surrounding. The assumptions of streams and unit operations are made as below. APR is chosen as the thermodynamic package as it is suitable for natural gas and soft two-phase system with high efficiency. After looking at this complete simulation setup, let's explore it step by step. Pure methane stream enters the compressor to increase its pressure, followed by a heat exchanger to raise the temperature of the methane gas. Water stream enters the pump to increase its pressure, followed by a heat exchanger to turn into vapor phase. After combining the methane and water stream with mixer, the mixture enters the steam methane reformer at 700 degrees Celsius and 1013 kPa. Endothermic reaction occurs in which methane is mixed with steam to produce hydrogen and carbon monoxide with heat adsorbed. After cooling down the mixture through cooler, it enters high temperature water gas shift at 350 degrees Celsius and low temperature water gas shift at 200 degrees Celsius. Exothermic reaction occurs in which carbon monoxide mixes with steam to produce hydrogen and carbon dioxide with heat release. The mixture is then separated with a two-phase separator that produces 12726.3 kmol per hour hydrogen.
For the deviation error, the value of the percentage error is very high because of the value of volume in simulation and manual calculations are very different. This is because the value of conversion in the manual simulation is assumed and the value of conversion is calculated for the simulation. Also, in the simulation, we are using the PFR reactor, while in the manual calculation, we are using PBR. Sensitivity analysis is performed to discuss the effect of temperature, pressure, feed flow rate, and composition on reactor performance. For the effect of temperature on reactor performance, the increase of feed stream temperature in each reactor increases the heat energy out of the reactor because more heat energy required to be released and absorbed during the reaction since the temperature is difficult to be maintained. In high temperature shift, the increase in temperature of the reactor feed stream decreases hydrogen mole fraction at the outlet stream because the reaction in HT shift is exothermic and does not favor high temperature. Thus, the hydrogen production is low. Next, the effect of pressure on reactor performance shows that when the pressure increases, the heat energy in SMR and LT shift decrease, but the HT shift heat energy increase. At HT shift reactor, the hydrogen mole fraction increases as the pressure increases because higher pressure increases the conversion of carbon monoxide to produce more hydrogen as the product. The third one is the effect of feed flow rate on reactor performance. The sensitivity analysis of the feed molar flow rate is carried out based on steam to carbon ratio, which is 3.2. It is observed that the increase in feed flow rate increases heat energy flow in the energy stream of each reactor, since there is more energy needed to be released or absorbed to maintain or reach a certain temperature. In SMR, the mole fraction of carbon monoxide produced increase when the feed flow rate of both methane and water increase. So, more carbon monoxide react with water and enters the HT shift to produce more hydrogen. The last sensitivity analysis is to study the effect of feed composition on reactor performance. Based on the figures shown, the LT shift outlet hydrogen molar flow rate increased with increasing methane fraction and decreased with inlet water fraction. Besides, SMR energy increased with inlet methane fraction and decreased with water inlet fraction. The increase in inlet methane fraction also increased the SMR outlet fraction, carbon monoxide, and LT shift outlet molar flow hydrogen because the methane to steam ratio increased. Hence, higher collision frequency increased the rate of reaction and greater amount of carbon monoxide and hydrogen are produced.
Moving on to the hydrogen enrichment unit. The type of hydrogen purification unit chosen is the pressure swing adsorption unit. This unit is constructed of high quality low alloy carbon steel due to its low tensile strength and high durability. Also, it is less prone to corrosion and able to withstand high pressure. For the configuration of the separation unit, a 2-bed 6-step system is used. This system works at a constant temperature to perform the adsorption and desorption process by alternating the pressure. The impurities are adsorbed to the adsorbent at high pressure until the equilibrium loading is reached. When low further adsorption capacity is available, the impurities are dissolved by lowering the pressure to regenerate the adsorbent. The whole process is summarized in the 6-step cyclic cycle as shown here. Then there are two adsorbents used, which are the activated carbon and G2-5. Activated carbon is a cheap and highly porous material that provides a large surface area to adsorb impurities from the mixture, whereas G2-5 has a high adsorption and desorption rate as well as a high cross strength. It is also excellent in removing polar components such as CO2 and CO. In the adsorption beds, the activated carbon is placed at the bottom as a primary adsorbent to reduce the amount of CO2 adsorbed into the second layer of G2-5 as the CO2 is hard to dissolve from G2-5 during the regeneration process. For the adsorption isotopes, these are the graphs of the amount of gas adsorbed at 25 degrees Celsius on the activated carbon and G2-5. According to the graphs, it can be seen that the lingua isotope is the best model that can fit the data for a combination of 4 gas components on activated carbon, while for the G2-5, the best model is the LRC isotope as its steepness of the adsorption rate reduces and increases pressures from the graph. Moving on to the physical properties of the adsorption columns, there are only 4 components present in the inlet gas mixture, which are H2, CO2, CO, and CH4, as the water is assumed to be removed before entering the column. According to the reference, the feed pressure and operating temperature temperature of the columns are set at 10 atm and 298 Kelvin respectively. Next, the height of the adsorption beds is 100 cm with a carbon to jalide ratio of 0.65. Additionally, the internal and external diameters of the beds are 3.71 cm and 4.245 cm respectively. The push to fit ratio is assumed 0.125 as the hydrogen with purity of 99.90%. Recovery of 56.17% is obtained from the article.
For the calculation part in the special process 2, we are going to do a calculation for mass surface zone for each adsorbent, namely activated carbon and zeolite 5A. Starting off from the figure of breakthrough curve of carbon dioxide on activated carbon, we can determine the breakpoint time Tb and the ideal adsorption time Ts by taking the value from the intersection between the breakpoint concentration of 0.165 and 0.5 with the breakthrough curve. Therefore, the value of breakpoint time Tb is 12 minutes while the value of ideal adsorption time Ts is 23 minutes. After converting from minutes to second, the height of used bed HB will be calculated using the formula here, and by substituting the values earlier, we will get the height of 33.9 cm. Lastly, by subtracting the values of total height with the used bed, we will get the unused bed or MTZ is equal to 31.1 cm. Then moving on to the second adsorbent, which is the zeolite 5A, from the figure of breakthrough curve of carbon dioxide on zeolite 5A. By using the same methods as on the activated carbon, we will get the value of breakpoint time Tb is 80 minutes while the value of ideal adsorption time is 27 minutes. And after converting the units and obtaining the value for used bed, we will get a total height of 11.7 cm for zeolite 5A, which is smaller than the MTZ for the activated carbon. For the strategies to achieve 99% purity of hydrogen production, firstly, for the adsorption column, the temperature of the adsorption unit must be lowered. This is because at lower temperature, the molecular kinetics of gas become less dynamic and thus allowing the gas to be readily absorbed by the adsorbent. Next, the pressure of the adsorption unit must also be increased. This is because when the pressure is increased, the adsorbate will stick to the adsorbent's surface more strongly and gases will also be forced to be trapped in the pores of the adsorbents. Other than that, the surface area of the adsorbents must also be increased by using other adsorbents with much larger surface area. This is because as the surface area increases, the adsorbing size also increase, allowing more adsorbate to be adsorbed at the same time. Moving on to the desorption column, firstly, the temperature of the desorption column must be increased. This is because at high temperature, the desorption rate is much higher. Next, the pressure of the inlet gas must also be lowered. This is because gases mixture will escape from the adsorbent much easier when the pressure is reduced. Lastly, by introducing a purge gas, the partial pressure of each component will be further reduced. In conclusion, for this integrated project, we have discussed the design of our SMR process that will yield the hydrogen production of 30,000 tons per year with a purity of 99.9%. In the reaction engineering part, we are using the packed bed reactor to allow a high conversion per mass of catalyst. We have also discussed the high temperature shift HTS and also the low temperature shift LTS that is run in the WGS reaction. Other than that, we have also determined the volume of each reaction and also developed strategies to maximize the selectivity and yield of hydrogen, which is by increasing the temperature, decreasing the pressure and increasing the ratio, and also utilizing the fluidized bed membrane reactor FBMR. For process modeling and simulation part, we are using the simulator software to conduct the simulation of the process. We have also calculated the deviation and error for the simulation and the manual calculation from the RE part. Other than that, we have also discussed the effect of temperature, pressure, flow rate and composition on the chosen dependent variables. For example, when the temperature increases, the heat energy flow in the reactor increases linearly while the hydrogen mole fraction decreases. And finally, in the separation process part, we have chosen the pressure swing adsorption unit PSA as the purification unit. We are also using low carbon as the material and a configuration of dual bed 6-step for the adsorption unit. The adsorbent chosen is activated carbon and zeolite 5A. We've also discussed the isotope that is suitable for this process, and lastly, we have also discussed the strategies to achieve 99.9% purity of hydrogen, which is by decreasing the temperature of adsorption unit, increasing the pressure and increasing the surface area. In short, for this intake project, we have achieved the objectives of each part. Several recommendations were also given for future plans, such as utilizing renewable resources such as biomass, and also by employing technologies such as pulsing electric fields and ultrasonic fields to improve the efficiency.